Hello there, and today I'm going to be talking us through a moments question from Edexcel past paper in January 2011, and this was question 3. Now, we're given the diagram in this question, and we're also told a little bit extra information. So, a uniform beam that goes from A to B has length 6 meters and mass 20 kilograms. Now, the fact that this is a uniform beam tells me that the mass of the beam, which is 20 kilograms, must act in the center of the beam. So I could draw the force on the diagram that's given to me. If I was to make a mistake, then this diagram that they've given me could get a little bit messy. So I'm just going to draw a brand new diagram from scratch. It wouldn't take us too long in an exam to do this, and that's just in case I was to make a mistake when drawing the diagram. So I'm going to draw my beam from A to B, and because this is a uniform beam, the mass of 20 kilograms, which would be a force of 20 times G, will act in the middle of the beam. So that's 3 meters from A and 3 meters from B. Now the beam rests in equilibrium in a horizontal position on two smooth supports. One is at C and one is at B. And it tells us that AC, this distance here, is equal to 1 meter. The other end is at B as shown in figure 1. And the beam is modelled as a rod. We have to find the magnitudes of the reactions of the beam at B and C. So because this rod is resting on two supports at both C and B, there's going to be a reaction force pointing upwards. Now, it doesn't specify that these are the same, so we have to assume that they're not. So I'm going to label this one reaction force at C, and I'm going to label the reaction force at B RB. And the first part of the question for 5 marks is to find the reaction force at both C and B. Now, because there's two unknowns here, I'm going to need two simultaneous equations to find the value of C and B. We could get these either by taking moments about two separate points on the beam, or we could just do one moments equation and get the other equation from resolving vertically, and that's what I'm going to do. So I'm going to make it clear to the examiner at this point that I'm going to resolve vertically. So I'm going to write R with an arrow, and that's just me telling the examiner I am resolving vertically. And because this system is in equilibrium, the forces acting in the upward direction, so that's RC and RB, they must be equal to the force acting downwards, which is the weight of the rod, which is just 20G. So my equation will be RC plus RB, they're the forces acting vertically upwards, that's equal to the forces acting vertically downwards, which is 20G. I'm going to label this as equation 1. So that's one equation with two unknowns. Obviously, to find these, we're going to need to use another equation. And what I'm going to do is I'm going to get that second equation from taking moments. Now, I could do that about any point on the beam, but I'm just going to choose the point B. Okay, and the reason I've done that is that eliminates the reaction force at B. So I'm going to have an equation involving RC going clockwise and 20G acting anticlockwise. And remember, for any moments equation, the moment of a particular force is the magnitude of the force multiplied by the distance it is acting from the point we're taking moments about. So because this system is in equilibrium, I can equate moments acting in a clockwise direction equal to moments acting in an anticlockwise direction. So in a clockwise direction, I have the reaction force at C, and that is a total of 5 meters from B. So the moments, again, I'm going to make it clear to the examiner, the moments at B, I'm going to have in a clockwise direction, RC times 5 meters, and that is going to be equal to the moments acting in an anticlockwise direction, which is going to be 20G, and that is acting at a distance of 3 meters from B. So RC times 5 is 20G times 3. Now this obviously means RC is equal to 60G, and dividing both sides by 5 tells me that the reaction force at C is equal to 12 times G. Remember, I'm going to be using G is 9.8 here, 9.8 newtons. So RC is 12 times G, which if you were to work that out with your calculator would give you 117.6 newtons. Now what I'm going to do is I'm going to use equation 1. Given that RC and RB add up to 20G, that tells me that RB, the reaction force at B, must be equal to 20G, take away 12G, which is 8G. And if you were to work that out again in your calculator, that would be 78.4 newtons. Now the way the mark scheme would allocate marks here, they would give you one method mark for each of the equations that you set up. So for resolving vertically and making it clear that I'm doing that, you get one method mark. And for taking a moments equation, you get another method mark. Now you will also get an accuracy mark if you do the correct moments equation, because sometimes these can be fairly easy to make a mistake on. And you would get the other two accuracy marks for solving each equation to get the value of RC and the value of RB. So in total, that there is 5 marks. Now moving on, there's a second part to this question. And it says, a boy of mass 30 kilograms stands on the beam at the point D. The beam remains in equilibrium, and the magnitudes of the reactions at B and C are now equal. So what I'm going to do is, because the situation has changed, I'm going to draw a whole new diagram from scratch. And I think this would be a very good idea, because it makes it easier for you to avoid making mistakes. So drawing my beam, again, this is the beam, and it goes from A on the left hand side to B on the right hand side. I have a support at C and a support at B, and this distance, remember, is 1 meter. The beam is still uniform, which means this mass of 20G will still act in the middle. I have no idea where the point D is on the beam, so I'm just going to label this point here D, and obviously where this boy is standing I have a force of 30 times G acting downwards. Just remember that it's not just 30 kilograms, the force acting is going to be 30 times G, which again we're going to be using G is 9.8. Now it tells us that the reactions at B and C are now equal. So same as before, at each of the supports there's going to be a reaction pointing upwards, but this time they're the same. So I'm just going to set them both as the value of R. And the question for 5 marks is asking us to find the distance AD. So the distance from the end A to where the boy is standing at D. So I'm just going to call that X. Now, same as before, this system has two things we don't know. We don't know the reaction force at C and B, and we don't know the distance from A to D, which I've labelled as X. So what I'm going to do is, because we need to find two unknowns, I'm going to set up and solve two simultaneous equations. Now, similar to before, the first one I'm going to get by resolving vertically. So the system's still in equilibrium, so it's still true that the forces acting upwards, which are the reaction forces at C and B, are the same as the forces acting downwards, which is the mass of the beam and the mass of the boy. So forces pointing upwards, I have the reaction force at C and the reaction force at B, which are both equal to R, and that is equal to the mass of the boy acting downwards and the mass of the beam acting downwards. So this tells me that 2R is equal to 50G, so therefore R is equal to 25 times G. So now that I know R, I can, on my diagram, I can set this is 25G, and the reaction at B is also 25G. Because I need to find the distance x, the distance from A to D, I'm now going to take moments about the point A. And because the system is in equilibrium, I know that the moments acting in a clockwise direction, which are the forces acting downwards, that's going to be equal to the moments acting in an anti-clockwise direction, and they're coming from the reaction forces. And again, remember, moments is equal to the magnitude of the force times the distance from the point you're taking moments about. So if we start off looking at our anti-clockwise forces, I'm going to have the reaction force at C, which is 25G times 1. And I'm also going to have the reaction force at B, which is 25G times 6. Remember, C is 1 meter from the end A, and B is 6 meters from the end A. Now that is equal to the moment acting in a clockwise direction. So we're going to have the weight of the buoy, which is 30G, times the distance of x. So I'm going to put 30G times the distance of x. And we've also got the weight of the beam, which is 20G, acting a distance of 3 meters from A. Now, at this stage, I haven't actually made it clear to the examiner where I'm taking moments about. So just to make it a little bit clearer, I'm going to just write moments at A. Now, simplifying this equation first, on the left-hand side, I will get 175G, and on the right-hand side, I'm going to get 30Gx plus 60G. Now I can cancel out the G's, I can divide the whole thing to cancel out the factor of G. If I was to bring this 60 onto the other side, it tells me that 115 is equal to 30x. And dividing both sides by 30 tells me that x is equal to 3.83 meters. And we wanted the distance AD, the distance from A to D, which I labelled as x, and that is equal to 3.83 meters. Now, to tell you where the marks in the mark scheme are allocated for this, you get one B1 mark, which just means a completely unrelated mark that isn't affected by anything else, for finding the new reaction force. Now, taking moments anywhere on the beam to help find this distance x gets you a method mark. And because this is a fairly complicated equation, it would be very easy to make mistakes, you also get 2 accuracy marks for doing it correctly. And then solving this to get your final answer is where the 5th mark comes from. So a total of 5 marks. And that was January 2011, the Edexcel M1 paper, question 3. Thanks for watching. I hope to see you sometime again soon.